Hello, I'm Seema and welcome to part 2 of the chapter, The Solid State. In part 1, I told you that we can classify solids into crystalline amorphous solids on the basis of the kind of arrangement of their constituent particles. We are now going to classify in this video solids into 4 different categories based on their constituent particles. What the constituent particles are like and what the kind of bonding is between them. So on the basis of their bonding or the constituent particles, we can classify solids into 4 main categories. These categories are molecular solids, ionic solids, metallic solids, and covalent or net. Hello, I'm Seema and welcome to part 2 of the chapter, The Solid State. In part 1, I told you that we can classify solids into crystalline solids and amorphous solids on the basis of the kind of arrangement of their constituent particles. We are now going to classify in this video solids into 4 different categories based on their constituent particles. What the constituent particles are like and what the kind of bonding is between them. So on the basis of their bonding or the constituent particles, we can classify solids into 4 main categories. These categories are molecular solids, ionic solids, metallic solids, and covalent or network solids. So let us just jump into it and see what these different kinds of solids are. The first type is the molecular solid. As the name suggests, the constituent particles in these solids are molecules. Molecules make up these solids, and these are further classified into 3 categories, that is non-polar, polar, and hydrogen bonded. Because molecules can be polar molecules, they can be non-polar, and they can be in the presence of hydrogen bonding, which is again a special kind of one of the forces, that is the London dispersion force, which is seen in solids. Let us understand these. Non-polar solids first. Non-polar solids are solids in which you have molecules. The molecules may be monoatomic, they may be diatomic, they may be polyatomic, but these molecules are made up of atoms which have almost similar electronegativities. So what happens when such molecules are formed? If let us say there are 2 atoms, the 2 atoms have almost similar electronegativities, so when they combine, none of them has a tendency to pull the electrons towards itself and become slightly charged, slightly negative. And if 2 atoms that are bound together have different electronegativities, then the one that is more electronegative has a tendency to pull the electrons towards itself, thereby acquiring a negative charge. And due to that pulling away the electron from this other species, that other species becomes slightly positively charged. So a polarity develops in the molecule. The molecule becomes polar. Why polar? Because positive and negative charges are separate in such a molecule. So when you say a molecule is non-polar, it means the atoms that are making the molecules, they have almost the same electronegativity, and therefore the charge separation is not there in such molecules. So what kind of forces are going to hold such solids together? Remember, whenever there is charge separation, the Coulombic forces or electrostatic forces of attraction are the strongest forces of attraction. That is, the positive and negative charges, when they attract, they really attract strongly. An example is, imagine how strongly is this door or this wall attracting me? Not much. But if you try to put your finger into a plug which has electric current, which has positive and negative charges, you would get a strong attraction. If it is direct current, you're going to stick to it. So wherever there is a charge separation, the attraction is much more. So if you imagine a solid which does not have any charge separation, the molecule is not polar, the attraction between molecules would be very weak. And since the attraction between these molecules would be very weak, what are the properties that would be affected? First of all, what kind of attraction is going to hold these together? The kind of attraction that is going to hold these non-polar molecules together is going to be London dispersion forces. And in class 11, you've done the intermolecular forces. The least the weakest kind of forces that exist are the London dispersion forces. So such solids would be really weakly, very weak forces are holding them together. So these solids are going to act as solids at very, very low temperatures, because even at room temperature there is enough heat and enough energy moving around that is going to give so much kinetic energy to the molecules that they will either be present as liquids or they would be present as gases. But if you want them as solids, you will really, the energy has to be really low to keep them as solids, so that a force as weak as the London dispersion forces can hold the particles, the molecules together to keep it as a solid. Because in the solid state, the molecules should be bound to each other, they should be fixed at one position, which is only possible when they are holding on to each other strongly. So that is possible only at very, very low temperatures, where these molecules can be stuck and they can act as solids. So what do we understand? That these non-polar molecules are where the constituent particles, of course, are molecules. The forces of attraction that hold these molecules together are the London dispersion forces. They would be very soft solids. They wouldn't be hard, because the stronger the forces of attraction, the harder would be the solid. And since the forces of attraction are the weakest, these would be the softest solids. And would they conduct electricity? Understand, to conduct electricity, a substance must have positive and negative charges which can move. Moving charges, charge that is moving, is electricity. So if the charges cannot move, even if a particle or molecule has positive and negative charges, if the charges are not free to move around, that substance cannot conduct electricity. And since non-polar solids are solids where molecules do not have charge separation, they do not have a separation of positive and negative charges, obviously such molecules would be insulators, they would not conduct electricity. Then what about the melting point? They have very low, obviously they would have very, very low melting points, because the London dispersion forces would allow them to act as solids itself at very low temperatures. So they obviously have very, very low melting points, or rather the lowest among all the solids that we would be studying. Let us take a few examples of this kind of solid. Examples are argon, carbon tetrachloride, hydrogen molecule, iodine molecule. You see, these are molecules which have the same element, two atoms of the same element. Obviously, no electronegativity difference. They are both identical, no charge separation. So they would be non-polar molecules. Carbon dioxide, these are all examples of non-polar molecules, and they would act as solids at low temperatures. The next kind of molecular solid is a polar molecular solid. Again, the constituent particles are molecules, and as I explained to you, if the electronegativity difference is more between the atoms which are present in the molecule, the more electronegative atom would pull the electrons towards itself and become negatively charged. And the remaining atoms from which it attracted the electron would become partially positively charged. Therefore, a charge separation occurs. Now, whenever you have positive and negative charges, the positive of one molecule will attract the negative of the neighboring molecules, and the negatives of those molecules will attract the positives of all the neighboring molecules. So all molecules will attract each other due to opposite electrical charges. And I also told you that electrical forces of attraction, or Coulombic forces of attraction, are the strongest. Therefore, whenever you have that partial positive, there will be attraction, but it is not so strong as you would have in ionic solids. In ions, you have a proper positively charged cation, positively charged anion. The positive is going to remain positive, the negative is going to remain negative. That is not there in the case of polar solids. They are only partially positively charged because they have more electronegativity, so the shared pair of electrons, they are pulling it slightly more towards itself. But they do not completely own, they do not completely take away the electron from the other atom. So there are Coulombic forces of attraction which are holding them together, therefore they would be stronger solids than the non-polar ones. So what do you have? The bonding attractive forces which are holding these together are dipole-dipole interactions. These dipoles may be temporary dipoles, they may be permanent dipoles, but these dipoles are not like ions. They are not, complete transfer of electrons is not there. So they are stronger than non-polar molecules, but they are weaker than ionic solids. So such solids, they have dipole-dipole interactions which are holding them together. What are the examples of this kind of solids? You have hydrogen chloride, sulfur dioxide are examples of dipole-dipole interaction. How would they be? They would also be soft solids because they are not ionic compounds, they are not crystals, they do not have complete ions, and therefore the electrostatic forces of attraction will be strong when there is a complete charge separation. Here it's only a partial, they are only partially positive, partially negative. Therefore the charge separation is not so drastic, and therefore these would also be soft solids. Would they conduct electricity? There is charge separation, but these charges, what partially positive and negatively charged atoms, they are combined together by covalent bonds in the same molecule. Within the molecule, they are held together by covalent bonds. So if something moves, if the charge moves, the entire molecule will move. So it is not, now electricity will be conducted when positive charge goes in one direction and negative charge goes in the other direction. But if the whole molecule is moving, then the positive and negative are moving together. Therefore, that cannot conduct electricity. So we say that they are also insulators, because although there is charge separation, there is not total charge separation, and the charges are not free to move on their own in a certain direction. Therefore, these are also insulators. And since they are also not very strongly bound together, the weak dipoles or dipolar forces are only holding them together, they would also be soft solids, and since they are soft solids, their melting points would also be low. And they are also usually liquids or gases at room temperature. You would find them to be solids only at lower temperatures. The next category of molecular solids are the hydrogen bonded solids. The hydrogen bond actually is not a bond. We've done chemical bonding and molecular structure in class 11, and I told you at that time the hydrogen bond is not a real bond. The hydrogen bond actually is a kind of a polar covalent bond, but the polarity is so extreme, is such an extreme polarity that it kind of acts as proper ions, and the attraction between the poles, that is hydrogen and the other atom, the positive and the negative, is not an ionic attraction, but it is stronger than the dipole-dipole forces. It is stronger, it is a very strong kind of a dipole interaction, and that is why, although it is just an attraction, we call it a bond. It is not an actual bond, yet we call it a bond because the force of attraction is stronger. So when does hydrogen bonding take place? Hydrogen is an electropositive nonmetal, and the most electronegative nonmetals are in the first period. That is, you have nitrogen, oxygen and fluorine. These are the three most electronegative nonmetals. So what happens when hydrogen, which is the most electropositive nonmetal, it forms a covalent bond with any of these three most electronegative negative atoms or elements, the electronegativity difference is maximum in this bond, because hydrogen most electropositive and these three elements most electronegative. So the polarity that is created is the maximum that is possible in the entire periodic table without making it an ionic compound. So there is a covalent bond, but the tendency of hydrogen to attract the electrons towards itself is much stronger. So the dipole is created, and I've drawn a structure of this. You have a hydrogen bonded molecule is water, for example. In water molecule, oxygen is attached to hydrogen. Wherever there is a bond between hydrogen and an electronegative atom like oxygen, nitrogen or fluorine, hydrogen bonding exists. So when you have two molecules of water, like you have one molecule of water here, one molecule, the oxygen, which is electronegative, gets attracted to the hydrogen of the neighboring molecule. And this attraction is also very strong, so we call it a hydrogen bond. So in this way, the water molecules, the hydrogens and oxygens of different molecules form hydrogen bonds among themselves, and it creates a network of water molecules which turns it into a solid. And that is what happens when ice is formed. When ice is formed, the hydrogen bonding is present, and remember, hydrogen bonding the bond is not a proper bond. It is an extreme case of London dispersion force or the dipole-dipole interaction. Therefore, this kind of a bond that we call has more distance than the normal OH bond in water molecule. So the distance between the oxygen and hydrogen of the hydrogen bond is more, and the distance between the hydrogen and oxygen of the molecule, which are bound by covalent bonds, is less. So what happens? What is the effect of this? What is the result of this? Have you noticed that when water turns into ice, it expands? And that's the reason why when you put ice in water, the ice floats over water. Because when water turns into solid ice, the hydrogen bonds increase the distance between the molecules, and therefore the density of ice decreases and it starts floating on top. Just an additional information because it's interesting, and it has something to do about, it will give you an idea about the hydrogen bond, how the distance increases. So solids which have hydrogen bonds, that is the third category of molecular solids. So they have hydrogen bonding. Example is water, ice. What kind of a solid is it? You know ice, you have to crush it. It's a hard solid. It is present as a solid at room temperature. Sorry, not at room temperature, at 0 degree. It is also not present at room temperature. Water is present at 0 degrees Celsius. Below 0, it is present as ice. And does it conduct electricity? Although there is polarity, there is no complete total separation of charges or total transfer of electrons. Therefore, the ions cannot move, the electrons and the positive charges cannot move individually, and therefore that is also an insulator. So that was about the molecular solids. The next category of solids are the ionic solids. Ionic solids, what will be the constituent particles of ionic solids? Ions. You already know what an ionic bond is. When you have positively charged, for example, you have sodium chloride. Sodium chloride crystals are cubic crystals, kind of, where every sodium is surrounded by chlorines. How many chlorines? Let us take this chlorine. This chlorine has 1, 2, 3, 4 sodiums, and 1 sodium in front of the board and 1 sodium behind the board. So it has 6, it is surrounded by 6 sodiums. Similarly, every sodium is surrounded by 4 chlorines in the same plane, and 1 chlorine in front, 1 chlorine behind. So it is a network of positively and negatively charged particles and there is complete transfer of electrons from sodium to chlorine. Therefore, these are proper ions, and these lines that I have drawn are not actual bonds. They are just Coulombic forces of attraction. The only bonds, the meaning of bond is a shared pair of electrons. So only bonds are in molecular solids. You do not have bonds in any of the other, of course these you have, covalent or network solids have bonds. But ionic solids and metallic solids do not have chemical bonds. There is no shared pair of electrons in them. The ions are formed by complete transfer of electrons, and the ions stay together due to Coulombic forces. And these Coulombic forces are so strong that they keep the ions together, and they are rigid solids, they are hard solids. Example, you can take a Rubik's Cube, which is a very good example of sodium chloride, you know. If this is, let us say, chlorine, imagine the ball, the square in the middle of the cube, in the center. In front of it, it has a sodium. Behind it, it has a sodium if it's a chloride. And then on this side, on the 4 corners, it would have sodiums. So, or if you imagine this to be sodium, then it has chlorine here, chlorine here, chlorine here, chlorine here, chlorine in the middle behind it, and chlorine in front of it. So in that way, it is surrounded by 6 chlorines. And this is how you would have the structure of sodium chloride. A cubic structure, densely attached together, very well packed, and a solid. So that is the kind of an ionic solid that you would have. What are the kind of forces that hold the ionic solids together? It is the Coulombic or electrostatic forces of attraction. Examples of ionic solids are sodium chloride, magnesium oxide, zinc sulfide, calcium fluoride. Now, these solids are hard, but they are brittle. If you crack them, crush them, they they form crystals. And I told you in the previous video, I told you about crystalline solids. They have got certain planes, they've got certain structures. So they form crystalline solids which are hard, but they are brittle. And ionic compounds do conduct electricity, but not in the solid state. They can conduct electricity. Why? Because for conduction of electricity, the ions should be free to move. And in the solid state, they are tightly packed, they do not move. It's not possible for them to move. It's only when they are in the molten state or they are dissolved in water, that is when they would start conducting electricity, because now the ions are free to move, and when they move, they conduct electricity. So we'd say they are insulators when they are solids, but they conduct in the liquid state or in the aqueous states. What about their melting points? They are solids at room temperature and they have high melting points. They are pretty stable solids. The next category of solids are metallic solids. We know about metals. Metals are hard, they are strong. I do not see any metallic thing here right now. Metallic solids, they are, yes, I do have, playing along with a lot of gardening these days. So this is a metallic plate here, right? So metals, they are solids, proper hard solids. And what is the constituent particles of metallic solids? In metallic solids, the metal structure, if you see the molecular structure, they are positively charged metal atoms, and when they lose their electrons, these electrons, they start floating around in the metal. And when they start floating around, they form a sea of electrons. It is as if there's a sea of electrons in which the metal ions are embedded. So that is how it is present. Electrons can move. The sea of electrons, the electrons are mobile, although the metallic atoms are fixed the metallic ions are fixed where they are. And it is this quality of electrons which are free to move that make metals conduct electricity even in the solid state. So metallic solids are solids where you have positive ions in a sea of delocalized electrons. Delocalized means electrons which have moved from their own position. And this sea of electrons is available to conduct electricity. This kind of bonding is a special kind of bonding which is known as the metallic bond. Again, there is no bond here. But the electrons are free, and it is again the Coulombic forces of attraction, the positive and negative, which are going to keep the metal atoms together. The negative sea of electrons holds the positive metals together, metal ions together. So we say that this kind of bonding is known as metallic bonding. Example is iron, copper, silver, magnesium, gold, all metals. What is the physical nature of metals or metallic solids? They are hard, but they are malleable, they are ductile. Malleability and ductility you've studied in class 10 also. Anything that can be beaten into sheets is said to be malleable. Anything that can be heated and you start pulling it, it forms a wire. So anything that can be drawn into wires is said to be ductile. So metals they are hard, but they are malleable, they are ductile. And why are they malleable and ductile? That is also because of the metallic structure. The sea of electrons, as you start beating the metal, the electrons, they just move a little and they distribute themselves again, but they don't leave the metallic atoms. And the metals also just redistribute their positions and they still stay together to remain together. And since they remain together, they do not break off and fall off like glass does. So when you beat it with a hammer, it does not crack, it does not break, it only flattens. Why? Because it is only changing its position. The electrons are still going to just, it's a free floating electrons, they just rearrange themselves to again bind the metallic atoms together. And the same happens when you draw a wire. As you pull the wire, pull the metal atom, the electron starts moving with it, pulls the previous metal atom, and then the electron moves with it. It pulls the previous metallic atoms, and therefore as you keep pulling, it keeps forming a wire. So that nature also is due to the metallic bonding. So what about metallic bonds? They are hard, but they are malleable, they are ductile, and they are conductors in the solid and molten states. If they can be conductors in the solid state, they have free electrons to move around. In the molten state, of course, they have those free electrons to move around even faster. So they are good conductors. What about their melting points? As you saw, when you hammer it, when you put it under stress, it only changes its shape. It does not break and fall apart. So what would you imagine its melting point? And the forces of attraction, the Coulombic forces of attraction, are very strong. Therefore, the melting point of metallic solids is fairly high. The fourth category, the last category of solids, is the covalent or network solids. Now, these are solids which are kind of molecules, but these molecules are attracted or attached to each other by bonds which form networks. So the molecules, they form a web or a network of chemical bonds. So this kind of a network of chemical bonds or covalent bonds, such solids are known as covalent or network solids. Examples: diamond and graphite. Diamond, has a tetrahedral structure. A tetrahedral structure where you have one carbon attached to 4 other carbon atoms, and each corner of the tetrahedron further acts as the origin of the next tetrahedron. So you have the next tetrahedron. I've not used all 4, but I've just used a couple in each. So that forms another tetrahedron. The corners of the tetrahedron act as the origin of the next tetrahedron. Thus the network goes on expanding, and that results in the formation of a network of bonds. And the larger a piece of diamond, so you can imagine a piece of diamond, if you say, is bigger. The bigger it is, the bigger the molecule. The smaller it is, the smaller the molecule, because all of it is actually just one molecule, where you have a network of bonds which is holding it together. The next type of, it is the same. Another example here is graphite. And graphite, on the other hand, is also a network solid. But graphite is a little different from diamond, as we know in its structure. That graphite has got planar structures. It has got the network in one plane, in 2 dimensions. So in one plane you have these hexagons, a plane of hexagons forming a network. And then, like a page of a book, the second page is another plane of these hexagons, and the 2 planes, they remain attracted together. They remain together and are held together by forces of van der Waals forces of attraction, or London dispersion forces, which are weak forces. So that is the pencil lead that you have, the lead in a pencil. That is this is graphite, the lead of a pencil. And what happens? It has got this one layer and the second layer. So the tip would have one layer. Below it would be the second layer. So when you write on a paper and you try to write on a paper, it leaves a mark. Why? Because the molecules, the layers keep coming off. And as you keep moving the pencil, the first layer moves off, then the second layer, then the third layer. So quickly it keeps following. The London dispersion forces pull the next layer, pull the next layer. Therefore a continuous mark is formed, and we use graphite for writing. The pencil lead is actually graphite. So this is also a kind of a solid. Now, what are these covalent or network solids like? What are the constituent particles? Actually, they are only atoms. And atoms which are held by large networks of covalent bonds. So what is the kind of bonding they have? They have covalent bonding. And what are the examples? Silicon dioxide, which is quartz, is an example of such a network solid. Silicon carbide, carbon in the form of diamond and graphite. And aluminum nitride is also an example. What is the physical nature of these solids? They are hard, but graphite, on the other hand, is soft. because graphite actually is an exception. It is a network solid, but because of this forming the solid in layers or forming the bonds in layers, it has certain characteristic properties which make it kind of an exception in the network solids. But others are like diamond. Diamond is the hardest known substance. So such solids are usually hard except for graphite, which is soft, and that is because of its unique structure, layered structure. Now let us talk about their electrical conductance. The covalent or network solids, usually they are insulators. Why are they insulators? Because as you see, the network of covalent bonds, and they are all identical atoms, there is no charge, especially in diamond, there is no charge separation there, and since there is no charge separation, no charged particle free to move about, therefore network solids do not conduct electricity. So they are insulators and their melting points are very high. But the exception in this category is graphite. Graphite, although it is a network solid, it is an excellent conductor of electricity. And the reason, it is a little confusing, graphite, although it has the best of both the worlds. It has delocalized electrons in its network. You know, every carbon has a valency of 4. It can form 4 bonds. But if you look at a carbon in graphite, it forms only 3 bonds with the other carbons. And one electron is such whose valency has not been satisfied, or rather whose the octet or the pairing has not been satisfied. So those electrons, the 4th electron, it becomes delocalized and it becomes free to move about. And since it starts moving about, it is somewhat like the metals, where the electrons get delocalized and they start moving in a sea of electrons, but it is not exactly like metals. This is more like aromatic compounds, where electrons, they get delocalized so that it can satisfy its deficiency of one electron, more like aromatic compounds. So these electrons which get delocalized, they are free to move about, and they cause the excellent electrical conductance of graphite. And that's the reason why graphite is a very good conductor of electricity. And what about the melting point of graphite? Graphite also has a very high melting point. So these were the different categories of solids on the basis of their the constituent particles. And with this, I'll finish this video. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos. Hello, I'm Seema, and welcome to part 3 of the chapter, The Solid State. In this video, I'm going to tell you about crystal lattices and unit cells. Imagine when you have to make a building, what do you need? You need bricks, and these bricks are arranged in a certain way. And when you arrange these bricks in a certain way and expand that arrangement in 3 dimensions, you get a building or a structure that you are building. Like the Lego blocks that you had when you played with as kids, you join them in certain patterns and you get different structures. In the same way, when you have crystalline substances, in the crystalline substances, these bricks or the minimum structure in chemistry is known as a unit cell. And when you expand this unit cell in 3 dimensions, you get a structure, a pattern. That pattern is known as the crystal lattice. And the crystal lattice, when it follows a certain pattern, that particular substance exists in the form of a crystal, which has a definite specific shape, specific faces, and that is why you have diamonds which have a specific cut. They have specific surfaces. So that is the reason why crystalline substances have got definite structures, just as your arrangement of bricks in a certain way will make a building of one type, and if you had arranged the bricks in a different way, you would get a building of a different kind. Now, you could imagine the lattice to be somewhat like the Rubik's Cube. These are little cubes, and the little cubes have been all joined together. When you join these little cubes, each of these little cubes is a unit cell. And the unit cell, when you expand it in 2 dimensions, you get this one surface with 9 unit cells. And then when you expand it in 3 dimensions, you get this giant cube, a bigger cube. And the cube is nothing but the expansion of the same structure in all directions. Which gives, since the cube is a very symmetrical structure, what you get as a result of it is also a symmetrical cube. On the other hand, if the cube was, the unit cell, the cube was not a cube, it was, let us say, a cuboid, like this shoebox. If it was cuboidal, then the shape of the, if you had these as bricks, then the arrangement, how would you do the arrangement? This way, and how are you arranging the next brick? This way, or are you fixing it this way? So how you arrange the unit cells, in what pattern do you repeat it? That would make the crystal lattice. And that is why, based on the kind of unit cell that you have, you would get different kinds of crystal lattices, which would then cause different structures of different kinds of crystals. So that is the reason why different crystals have different shapes, they look different, their colors are different. Of course, that is due to their chemical properties, but the structures are different because of the difference in the pattern and the difference in the original unit, the brick itself. The brick could be a cube, the brick could be a cuboid, the brick could be a cuboid with tilted edges. Instead of all being 90 degrees, it could be slightly tilted. So how the unit cell is, there are different types of unit cells, and then these unit cells, how are they arranged in 3 dimensions to create different types of lattices. Now, the scientist who described these lattices, or there are 14 types of lattices, and they are known as the Bravais Lattices. And Bravais was the scientist after whom these lattices have been named. And there are 14 types of Bravais lattices which are created on the basis of the arrangement of these unit cells. So let us now understand the unit cells and the lattices better. A regular 3-dimensional arrangement of points in space, that is known as a crystal lattice. What are the characteristics of the Bravais lattices? Each point in the unit cell, or in the lattice rather, each point in the lattice, if you see each corner of each cube actually represents an atom. Each corner, we call them the lattice points. So each point is a lattice site or a lattice point. What does the lattice point mean? That whatever is the constituent particle which is making that crystal, it could be an atom, it could be an ion, it could be a molecule, whatever is the basic structure, molecular structure or atomic structure, which on repeating will give you first the unit cell and then the lattice. That unit is one corner of the cube, and these points are known as the lattice points or the lattice sites. I'll just give you an example. You can imagine, as I told you, that a cube would be the simplest kind of unit cell. And let me imagine that I have this set of balls, okay, the table tennis balls, and I'm placing them one over the other. When I place them like this, one over the other, can you notice you're getting cubes? You see 4 here and 4 here. And if you look here, you'll see these 4 will make one cube because there are 4 behind it and 4 in front, 4 white, 4 orange. Similarly, 4 orange and 4 white are in the back. So they're making a cube. These are making cubes, if you see. And then when you expand the structure, it results in the formation of a lattice. So how does it expand? Let me start expanding it now. So let me imagine that now, since I have these 2, now I have a 3rd layer over it. There, ball over ball, and a 4th layer over it. And now it is like placing the bricks. And the 5th layer over it. Do you notice? You will be able able to see the squares very clearly, the unit cells, the squares, and if you see, the squares are being repeated in all directions, resulting in that crystal lattice. So the unit cell actually is not a cube. It is only these balls, the constituent particles, and the cube is imaginary. The lines are imaginary. The lines are only drawn to give us an idea what the basic structure is, while in actuality you only have the particles, that is the constituent particles, which are present in a certain pattern, which gives you an idea what the unit cell may be. And then the unit cell expands and it gives you the entire crystal lattice. And I told you there are different kinds of lattices that are produced due to unit cells, and I'll just show you how. Do you